Welcome to the deep dive. Today we're looking at a source package that honestly draws one of the most surprising lines I think we've ever seen. We're connecting a computer from, what, 1985? The Commodore Amiga?
That's the one. A real classic.
And connecting that directly to, well, the absolute cutting edge of AI supercomputers being built right now. It feels like history finally catching up.
It's really quite something. The sources we have lay out this argument that the basic design thinking behind that, nearly 40-year-old machine, it wasn't just quaint, it was fundamentally correct for the kind of work AI demands.
We're talking about how that necessity is now forcing these huge technical shifts, things like this potential NVIDIA-Intel alliance the sources analyze as a thought experiment, and why these massive 1.8 terabyte per second interconnects are basically the Amiga's core ideas coming back.
Exactly. Reborn, you could say.
Okay, so that's our mission for this deep dive. Show how this sort of forgotten Amiga philosophy isn't just relevant again, but it's actually the bedrock of the whole AI infrastructure. And the central concept, you mentioned it, is heterogeneous computing.
Right, let's start there, because traditional computing, certainly through the PC era, was all about brute force, wasn't it? Get one big chip, the CPU, the central processing unit, and just make it faster and faster every year.
Moore's law in action.
Pretty much. But heterogeneous computing flips that script. It says, look, computing isn't one job, it's lots of different jobs. Some things like graphics or sound or network traffic or now, the matrix math for AI, they need specialists.
So you offload those tasks to dedicated hardware.
Precisely. You build a committee of specialists, each optimized for its own task, rather than trying to make one generalist chip do everything.
Okay, let's bring that committee to life. Let's talk about the original.
Yeah.
The Amiga. Launch 85, you said. And the dominant player then was the IBM PC, which was very much that CPU-centric, monolithic design. Why did the Amiga folks see it so differently?
Well, I think they recognized early on that rich graphical interfaces, multimedia, these things were just too much heavy lifting for the CPUs back then. The main processor, a Motorola 68000, it needed to be free just to run the OS, handle user input, the basics.
And that freedom came from the custom chips. The OCS.
The original chipset, yeah. That was the heart of it.
Okay, let's meet the team. First up was Denise, the graphics chip. The visual artist, as our notes say.
Yeah, Denise was the dedicated display processor, handled the Amiga's, for the time, incredible 4096 color palette. But the key thing, it managed up to 8 hardware sprites. Think, like characters in a game.
Right.
And the sources stress this, drawing them, moving them around the screen, zero load on the main CPU. Denise handled it all. If your main processor had to do that today, even with modern speeds, it would grind to a halt. Denise kept things smooth.
Okay, graphics covered. Then Paula, the audio and I/O maestro.
Paula was amazing for the time. It gave the Amiga 4 independent 8-bit PCM stereo sound channels, offloaded completely from the CPU.
Oh, it's channels.
Yeah.
And 85.
Yeah, so the computer could be playing complex music, sound effects, while displaying smooth graphics while you're interacting with the OS. And the whole thing felt responsive, because the CPU wasn't getting bogged down trying to mix audio or push pixels. The specialists were handling it.
So we've got these specialists doing the work, but they all need data, right? They all need to access memory. Which brings us to what the sources called the real linchpin, the ancestor of today's tech, Agnes.
Ah, Agnes. The address generator unites. Forget the name. Think of it as the system's master controller, the traffic cop for data. Its most critical job was managing direct memory access DMA.
DMA. Okay, why is that so important?
Because DMA lets the specialized chips, like Denise or the Blitter coprocessor, which was also inside Agnes, access system memory directly. Without bothering the CPU, they didn't have to ask the CPU to fetch data for them. They could go get it themselves. Agnes managed something like 25 DMA channels, giving everyone their own fast lane to memory.
Wait a second. If you have the CPU, Denise, Paula, the Blitter, all these things hitting the same memory pool at once, wouldn't that just be electronic gridlock? Constant collisions.
That's the million-dollar question, isn't it? And yes, it could have been. The Amiga used a shared pool of memory called chip RAM. Everyone could access it. The benefit was huge. No slow, manual copying of data between different memory areas. Everything was in one place.
But the cost was potential chaos.
Yeah.
Contention.
Exactly. And that's where Agnes's genius really showed. It solved the contention problem using interleaved access.
Interleaved access sounds like fancy scheduling.
It is, but baked into the hardware itself. Agnes didn't wait for requests and then try to sort them out. It synchronized the whole system proactively. It gave the custom chips priority during the odd memory access cycles, and the main CPU got the even cycles.
Like alternating traffic lights built right into the silicon.
That's a great analogy. It guaranteed the specialists could get their data predictably without stalling the CPU. This idea, preemptive, hardware-managed multitasking of memory access, that's the conceptual seed for the high-speed fabrics we use today in supercomputers.
It's almost, well, humbling. A consumer machine from the mid-'80s figured out parallel memory access, while the mainstream industry spent, what, the next 30 years focused almost entirely on making single CPUs faster?
It is pretty ironic, and the sources point out another irony. Eventually, to squeeze out more performance, the Amiga did introduce separate memory fast RAM that only the CPU could access quickly. This was meant to reduce contention on the main chip RAM.
And in doing so,
They created the exact same two-tiered memory problem that plagues modern systems. You have the super-fast private memory right next to the processor, like GPU RAM today, and then the slower shared system RAM that the CPU uses. History repeating itself.
so after the Amiga, the industry largely went down the other path. The monolithic CPU-centric road dominated by Intel and by '86, Moore's Law kept delivering faster CPUs, and for a long time, that worked, right? For basic stuff.
Absolutely. For word processing, spreadsheets, browsing the web, sequential tasks, making the CPU faster was the obvious path. It worked well for
And
decades.
then the nature of the work changed dramatically. AI arrived.
Exactly. And AI, specifically training neural networks, isn't sequential. It's massively parallel. It's all about doing the same simple math matrix multiplies, vector operations on huge data sets, all at the same time.
And the only chip architecturally suited for that kind of parallelism was the GPU.
The graphics processing unit. It already had thousands of simple cores designed for parallel work rendering pixels. Turns out that structure, often called SIMD, or single instruction, multiple data, was almost perfectly matched to the math needed for AI. NVIDIA saw this pivot early and ran with it, building CD. The GPU became the new star player.
But, and here's the catch, we plugged this incredibly powerful parallel engine into the system using the old plumbing, didn't we?
We did. We connected the GPU using PCI Express, or PCIe, which is fundamentally a general-purpose interconnect. It was never designed for this kind of workload.
It's like the main highway for everything else too, right?
Yeah.
Your fast storage drives, network
Yeah.
cards, and they all share that same PCIe bus.
Correct. And it's a hub-and-spoke design. The CPU, or its root complex, is the master controller. Everything else is a peripheral device hanging off it.
So you have this massive computational engine, the GPU, being treated architecturally like just another add-in card.
That's the mismatch. And in AI training, it becomes a severe bottleneck. GPUs are hungry, they need constant feeding with enormous amounts of data model parameters, training examples, intermediate results. But PCI just can't deliver it fast enough. The GPU ends up sitting idle, waiting.
Data starvation, that's the term. It's like owning a Formula One car but only being allowed to drive it in rush hour city traffic.
That's a perfect analogy. And it gets worse in systems with multiple GPUs. If GPU A needs to send data to GPU B, it can't talk directly. The data has to travel up the PCIe bus to the CPU's controller, then back down to GPU B. It congests the shared highway twice.
Something the Amiga's DMA and Agnes controller avoided 40 years ago by letting specialists talk directly to memory.
Precisely. The old solution held the key to the new problem.
Okay, so the industry hits this wall. The PCIe bottleneck becomes too painful, too expensive, especially for large-scale AI. And they're forced to rediscover the Amiga's approach. Build specialized communication for the specialized processors. This feels like the big aha moment.
It really is. And the answer, primarily from NVIDIA, was NVLink. Unveiled back in 2014, it's fundamentally different from PCIe. It's a proprietary, high-speed, point-to-point connection.
Point-to-point meaning direct connections.
Exactly. It lets processors, initially GPUs, but now other components too, talk directly to each other, completely bypassing that congested PCIe bus.
And the speed difference is just staggering. What are the numbers again?
The latest generation, with Blackwell, hits up to 1.8 terabytes per second of bidirectional bandwidth for each GPU. Compare that to, say, a fast PCIe Gen 5x16 slot, which gives you around 128 gigabytes per second.
So what, more than 14 times faster? That's not incremental.
Not at all. It's a different class entirely. And for you, the listener, if you're training a huge AI model, what that translates to is efficiency. Less waiting, more computing. GPUs spend more time doing useful work.
And it achieves this because it's not a bus like PCIe.
Right. PCIe is a bus shared lanes master-slave relationship with the CPU. NVLink creates a fabric Think of it like a dedicated network mesh where any connected GPU can talk directly and quickly to any other, often managed by specialized NVSwitch chips. It allows you to effectively glue multiple GPUs together into one giant virtual GPU.
Okay, so NVLink provides the superfast highway, but you still need a way to manage the data across these different processors smoothly. Which brings us to the software side, or the architectural concept. Unified Memory Architecture, UMA, the modern chip RAM.
That's the perfect way to think about it. UMA is the conceptual successor to chip RAM. It's about creating a single unified address space, a large tool of memory that both the CPU and the GPU can see and access as if it were one entity.
So, no more manual copying.
Hmm?
For decades, developers had to write code to explicitly copy data from CPU memory over that slow PCIe link into the GPU's private VRAM, and then copy results back.
Exactly. UMA gets rid of that headache. The hardware, using the high-speed NVLink fabric, handles moving the data automatically behind the scenes.
How does that work? Magic.
Sort of. It's called on-demand page migration. If the GPU tries to access a piece of data that happens to be physically located in memory closer to the CPU, the hardware automatically, transparently fetches that page of memory and brings it over the NVLink to the GPU's local memory, or allows access directly across the fabric.
Okay, so for a developer, this is huge. It simplifies the programming model immensely.
Immensely. You just allocate memory, and the system figures out where it needs to be for fastest access. It's what makes it practical to train models that are way too big to fit into a single GPU's memory. You can easily spread, say, a 200 gigabyte model across four 80 gigabyte GPUs, and the NVLink UMA system makes it feel like one giant 320 gigabyte pool of memory.
It's uncanny. The parallel is so direct. NVLink is the modern Agnes, the high-speed traffic cop and arbiter. UMA is the modern chip RAM, the unified workspace. And the goal is identical to 1985. Get the CPU out of the way and let the specialists work directly and efficiently.
And this technological reality, this shift back to heterogeneous principles, it inevitably drives major business strategy, which is where the source's analysis of this potential NVIDIA-Intel alliance comes in. It's framed as a technical necessity forcing a massive corporate realignment.
Right, let's unpack that hypothetical deal. Intel, the company that defined the CPU-centric era, potentially agreeing to embed its biggest rival's proprietary tech, NVLink, right into its core products. The sources call it a pragmatic surrender. Why would Intel even consider that?
Well, according to the analysis, it comes down to survival and relevance in the AI age. Intel was facing, significant financial pressure. A deal like this, with a suggested $5 billion investment from NVIDIA, provides immediate cash. But more critically, it offers Intel a fast track back to the heart of the AI build-out. Instead of fighting NVIDIA's interconnect, they integrate it.
So they pivot, away from being purely CPU-focused.
Essentially, yes. They leverage their strength in x86 manufacturing and design, but integrate NVIDIA's dominant GPU and interconnect technology. It's a way to make x86 central to AI again, but as part of NVIDIA's broader platform.
And for NVIDIA, why potentially pour $5 billion into a competitor? What's the strategic win, the masterstroke, as the analysis puts it?
Platform lock-in, essentially. NVIDIA already dominates AI training with GPUs and COD. The main friction point, the main bottleneck slowing things down, was a PCIe connection dictated by the traditional CPU architecture. By getting Intel to build NVLink natively into x86 chips, NVIDIA eliminates that bottleneck. The CPU stops being an external drag on the system and becomes a tightly integrated first-class citizen within the NVIDIA platform. It cements NVLink as the standard.
And the analysis suggests this leads to specific new products. First, for consumers, this x86 RTX SoC.
Yeah, this is fascinating. A system on chip bringing true heterogeneous computing back to the mainstream desktop or laptop. Imagine an Intel CPU chiplet and an NVIDIA RTX GPU chiplet sitting side by side in the same package.
But crucially, connected by NVLink, not PCIe.
Exactly. That's the game changer. It enables true UMA on a consumer device. Suddenly, the integrated graphics aren't starved for data bandwidth anymore because they have a high-speed link to the CPU and system memory. It could create a whole new class of powerful, efficient laptops.
And then for the data center, Intel designing custom Xeons with native NVLink.
Right, so Intel CPUs could plug directly into NVIDIA's high-end systems like their DGX servers, becoming fully integrated components rather than external hosts connected via slower links.
This really underscores that inversion of hierarchy you mentioned. In the AI world, the GPU and its fabric, NVLink, are the platform. The CPU becomes, in a way, a very powerful peripheral or co-processor, integrated into that GPU-centric system.
Precisely. It's still vital for running the OS, managing tasks, certain types of computation, but the center of gravity has shifted definitively to the GPU and its interconnect.
Okay, if this hypothetical alliance happened, the ripple effects would be huge. Who gets hit hardest? Let's start with AMD.
AMD is clearly in the crosshairs. They compete head-to-head with both companies. These new by86 RTX SoCs would directly challenge AMD's Ryzen APUs, which rely heavily on their integrated graphics performance advantage.
And in the data center.
NVLink native Xeons would be a direct assault on AMD's EPYC server processors, which have made huge gains, partly because they offered strong performance and connectivity options. But native NVLink integration is a different level for AI workloads.
What about ARM? They've been making inroads into servers and PCs.
This makes the climb steeper for ARM, especially in the data center. A big reason some companies considered moving from x86 to ARM was potentially better integration or efficiency for AI. If you can get top-tier AI performance and stick with your existing massive x86 software ecosystem via an NVLink native Intel chip, well, the incentive to switch diminishes significantly.
Keeps customers locked into the familiar x86 world, but now with NVIDIA's tech inside.
Exactly.
And finally, the analysis mentions TSMC, the foundry giant. How does this impact them?
The $5 billion investment isn't just cash, it's a signal. It suggests, according to the sources, NVIDIA might be serious about using Intel Foundry Services, IFS, as a major manufacturing partner.
A second source beyond TSMC.
A credible second source. That gives NVIDIA more negotiating leverage, reduces their dependency on a single supplier, and puts real competitive pressure on TSMC to keep their edge in pricing and technology.
Wow. Okay, this has been quite the journey. From a 1985 home computer to hypothetical multi-billion-dollar semiconductor alliances. But the connecting thread is clear. The Amiga's core idea, heterogeneous computing, spiralized processors working in parallel, managed by a smart interconnect, it wasn't wrong. It was just early.
Decades early, AI finally created a workload so demanding that the industry had no choice but to adopt that architecture. The hierarchy really has flipped. The interconnect, the fabric, is now king, defining the platform. The CPU, while still crucial, is now integrated into that fabric.
So the key takeaway for you, listening, is that the game has changed. Just having the fastest CPU or even the fastest GPU isn't enough anymore. Competitors need a platform strategy. That means a world-class, high-bandwidth interconnect like NVLink and a coherent memory architecture like UMA. That interconnect is the new toll booth. You have to pay to play at the highest level.
Absolutely. It's the price of admission for serious AI.
So we've solved one layer of complexity. UMA makes the programmer's life easier. No more manual data shuffling. But with these incredibly fast 1.8 terabyte per second systems, what's the next challenge for developers trying to squeeze out every last drop of performance?
That's a great closing thought. The challenge shifts, doesn't it? It moves from managing the mechanics of data movement to optimizing the locality of data. Even with UMA automatically moving things, performance still depends heavily on where data is physically located when a processor needs it.
So keeping data close to the core that's working on it.
Exactly, minimizing latency, even across that super fast fabric. With speeds this high, even tiny delays matter. So developers will need to become masters of data layout, cache utilization, understanding memory access patterns, ensuring the right data is in the right place at the right time. The hardware solves one problem, but it unlocks a new, perhaps more subtle software optimization challenge.
Fascinating. The quest for performance never really ends, does it? It just changes shape. Something to think about. Catch you next time for the next deep dive.